In this lesson, we're going to look at different ways to identify conic sections. In the table, we have the standard equations of the four conic sections. For example, in the circle, we notice that we are summing two squared terms. The denominators are the same, they're 1, and the right-hand side equals the radius squared. In the ellipse, we have the two equations depending on how the ellipse is oriented. Again, we are summing two squared terms. The denominators are different, and they are each equal to 1. In the hyperbola, we are again dealing with two squared variable terms, but we are taking the difference of those two squared terms, and they are each equal to 1. Denominators are different again. In the parabola, there is only one squared term. So this is what we are looking for in our equations. So in example 1a, you notice that there is only one squared term, so it is a parabola. In the second example, there are two squared terms, both the x and the y. The denominators are different, but more importantly, we are taking the difference, and the equation is equal to 1. So hopefully you recognize that this is a hyperbola. In example 1c, again we see two squared terms. We are taking the sum of two squared terms. The denominators are the same. The right-hand side represents the radius squared, so it is a circle. So if we have the equations in standard form, it's not so difficult to recognize which conic section you're working with. So what is the best thing to do? Put each equation in standard form. That way we can use these tricks to identify which conic section you're working with. In example 2, you have been given the equation in general form. So the first thing you want to do is you want to group your like variables. So we're going to take our x terms and have x squared plus 8x. Then you're going to group your y terms, which would be plus y squared minus 10y, and then we're going to take the constant and move it to the right-hand side. So we're setting it equal to 8. Now, with these square terms, what we want to do is complete the square so that we can easily factor it. What are we going to add to both sides with respect to the x variable? We'll take half of 8x, half of 8, the coefficient of x, which is 4, square it, and we're going to add 16. If you add 16 to the left-hand side of the equation, we have to add 16 to the right-hand side of the equation. Now we're going to complete the square with respect to y. Take half of negative 10, which is negative 5, square it, and we'll get 25. So now we're going to add 25 to both sides of the equation. If we factor this perfect square trinomial, we're going to get x plus 4 squared. If we factor this perfect square trinomial, we're going to get y minus 5 squared. And if we sum the constants on the right-hand side, we're going to get 49. So now we have our equation in standard form. We are summing two squared terms, so it is a circle. The right-hand side is not equal to 1. It is a circle. What is its center? Remember, that's HK, so that's going to be negative 4, 5. The next thing we have to identify is the radius. So we look at the right-hand side, it's 49, take the square root of that, and it's 7. And we can graph our circle. Label our axes. Our center's at negative 4, 5. And then from the center, we're going 7 units to the right, 7 units up, sorry, it's there, 7 units up, 7 units to the left from the center, 7 units down, and we can sketch our little circle. In the next example, we're going to look at this equation, and we see that it's not in standard form. So again, let's group our x terms. Let's group our y terms. And let's move our constant to the right-hand side. Now remember, to complete the square, you have to have a leading coefficient of 1. The leading coefficients are not 1, so we have to do some factoring first. Let's factor out a 5 from our x terms, giving us x squared plus 6x. And let's factor out a 20 from our y terms, leaving us y squared plus 2y. Now what are we adding to each of these to complete the square? We'll take half of 6, which is 3, square it, so we're adding 9. But we're not just adding 9 to the other side, we're adding 9 times 5, which is 45. In the case of the y, to complete the square, half of 2 is 1, squared is 1, but we're not adding 1 to both sides, we're adding 20 to both sides. So now let's factor that perfect square trinomial with respect to x, factor the perfect square trinomial with respect to y, and sum the right-hand side. Now, we want the right-hand side to equal 1. So we're going to divide every term by 80, and that is going to give us x plus 3 quantity squared over 16 plus y plus 1 quantity squared over 4, and the right-hand side is 1. Now we have our equation in standard form. We are summing two squared terms. The denominators are different, and it's equal to 1. So hopefully you recognize that this is an ellipse. So how is this ellipse oriented? Well, for an ellipse, the larger denominator is a squared. Larger denominator is under x, so it is horizontally oriented. If a squared is equal to 16, a is 4, and therefore we see the other denominator is b squared, so b is 2. So what is the center of our ellipse? HK, -3, -1. Let's plot that, -3, -1. That is our center. Now, it is horizontally oriented, so we're going to use the a value, 4, and from the center, we're going to go 4 to the right, giving us a vertex, 4 to the left from the center, giving us our other vertex. So we can label our vertices. Those points are -7, -1, and 1, -1. Now, how are we going to use B? B is going to give us our covertices. So we're going to go up 2 to get a covertex, down 2 to get a covertex, and we can label those points -3, 1, and -3, -3. So what do we have to do now? Well, we have to be able to find our foci. How are we going to find our foci? Well, for an ellipse, c squared equals a squared minus b squared. We know a squared, we know b squared, so we can find c squared, which is 12. So c is going to be the square root of 12, which is simplified as 2 times the square root of 3, which is approximately 3 and a little bit, 3.46. So from the center, I'm going to go 3 and a little bit to get a focus, 3 and a little bit to get our other focus. So we now see that our foci are what? -3 plus 2 times the square root of 3. Y value doesn't change, and -3 minus that c value, and the y value doesn't change. So now I can graph my ellipse. Now, looking at the next example, we see that only one term is squared. So we know what type of conic section this is. It is a parabola. We don't even have to do any work to identify that conic section because only one term is squared. So I'm going to go ahead and leave my y terms on the left, and I'm going to move all the other terms, the x term and the constant, to the right-hand side. Now again, we have to complete the square on the left. What are we adding? Well, half of 4 is 2, squared is 4. So we're adding 4 to both sides. Factor the left-hand side, combine our constants, but we notice the right-hand side isn't exactly in factored form. So I'm going to go ahead and factor the right-hand side, factoring out a 12, leaving me x minus 3. Now it is in standard form. Now how is it oriented? Since the y term is squared, it is horizontal. We can also identify p. So 4p equals 12, so p is 3. P is positive, so we know it opens to the right. So let's identify the vertex, HK. Be very careful because we know H goes with X, K goes with Y. So our vertex is 3, negative 2. We can plot that, 3, negative 2. There's our vertex. Now since the parabola opens to the right, I'm going to use that p-value, that distance of 3, and I'm going to go to the right 3 to get my focus. And I can label that point. That point is 6, negative 2. And I can also identify my directrix by going that same distance 3, but in the opposite direction from the vertex. 1, 2, 3, so we can see that our directrix is the y-axis. We have to write that as an equation. Now, the last thing we have to do is graph the parabola. So I'm going to use the equation, and I'm going to pick a y value, and I see that my range for this parabola is all real numbers, so I can choose whatever I want. I'm going to let y equal 0. No, I'm not. I'm going to let y equal 1. I can't choose, well, I could choose 0. Let's choose 0. Let y equal 0. So that's going to give me 4 equals 12 times x minus 3. Then I'm going to divide both sides by 12. So I'm going to get x minus 3 equals 1/3. I'm going to add 3 to both sides. So 1/3 plus 3, I got to get a common denominator. So that's going to give me 3 times 3, 3 over 3 here. I'm going to multiply. I'm going to leave that one alone. And this is 3 over 1, so I have to multiply it by 3 over 3. So that's 1/3 plus, what? 9/3. Gives me 10/3. So 10/3 is what? Well, a little bit more than 3. So when x is a little bit more than 3, y is 0. Using my axis of symmetry, I have another point, and I can graph my parabola. In this next example, again, it's not in standard form, so I'm going to group my x terms. I'm going to group my y terms, and I'm going to move my constant to the right-hand side. Now, to complete the square, what do we have to do? We have to get the leading coefficient to be 1, so I'm going to factor out a 4. What am I factoring from my y terms? A negative 9, leaving me y squared minus 4y. And we have to be careful that we're factoring out a negative. So what am I adding to my x terms to complete the square? Half of 2 is 1, squared is 1. What are we adding to the right-hand side? 4. How do I complete the square with respect to y? Half of 4 is 2, squared is 4. What are we adding to the other side? Negative 36. So if I factor each of those perfect square trinomials, and I combine my right-hand side, adding all those terms, I get this equation. Now I notice I'm taking the difference of two squared terms, so now I have to get the right-hand side equal to 1. So that's going to give me x plus 1 quantity squared over 9. minus y minus 2 quantity squared over 4, and the right-hand side is 1. Now it's in standard form. Since I'm taking the difference of two squared terms, the denominators are different, and the right-hand side is 1, it is a hyperbola. Now, how is it oriented? Well, I look at my positive term. Since my positive term is x, I know it is horizontal. Now remember, the denominator of the positive term is a squared. It's not the larger number. In this case, it is larger, but it doesn't have to be. So a is 3, b squared is 4, so b is 2. And of course, I can find c, but the relationship among a, b, and c for a hyperbola is a squared plus b squared equals c squared. So c squared is going to be 9 plus 4, c squared is going to be 13, and c is going to be the square root of 13, which is approximately 3.61. So let's identify the parts of the hyperbola. The center is at hk, negative 1, 2. I can plot that. There's my center. Now, where am I going from my center? Well, I'm going to use my a value and my b value, and I'm going to go ahead and count from my center. So, if I look at a is 3. So that is my distance from my center to my vertex. Since it's horizontally oriented, I'm going to go to the right 3, get a vertex, go to the left 3, get another vertex. So what are my vertices? Those points are 2, 2, and negative 4, 2. Now I have B. B is the distance from my center to my co-vertex. It's 2. So I'm going to go up 2 and down 2 from the center and get my co-vertices. And I'm going to label those points. My co-vertices are what? Negative 1, 4, and negative 1, 0. Now what am I going to do? Well, I have to use the C value to find my foci. My foci are on the same transverse axis as my vertices. So from the center, I'm going to go 1, 2, 3, and a little bit. There's my focus. 1, 2, 3, and a little bit. And there's my other focus. So what are those points? Negative 1 plus that C value. The Y value doesn't change. And negative 1 minus that C value, the Y value doesn't change. Now here I can draw my little rectangle passing through my vertices and my co-vertices. I can draw my asymptotes passing through the diagonal of that rectangle, and then I can actually draw my parabola. So what is my parabola going to look like? It starts at my vertex and hugs the asymptotes. There's one branch, and there's the other branch. So I have my hyperbola now. What is left? Let's write the equations of the asymptotes. Now, in this case, we see that the rise is going to be the B value. The run is the A value. So that's going to give me 2/3, plus or minus. Now, it's not centered at the origin, so I'm going to use the point slope formula. Y minus y1 equals plus or minus m, x minus x1, and the point I'm substituting in is the center. So the y value is 2. I know the slopes of those two asymptotes. The x value of the center is negative 1. Now at this point, I have two cases, when the slope is positive and when the slope is negative. When the slope is positive, I'm going to use this equation. When the slope is negative, I'm going to use this equation. Now, I'm going to distribute the slope in each of the equations. And I'm going to add 2 to both sides, because I want it in slope-intercept form. Then I'm going to get y equals 2/3 x plus, okay, then I have to get a common denominator, so 2/3 plus 6/3 is going to give me 8/3. There's one equation of the asymptote. And then y equals negative 2/3 x. Again, now I have to get a common denominator. So negative 2/3 plus 6/3 gives me 4/3. There's the other equation of my asymptotes. And we're done.